Okay, thank you so much for joining me in this part 1 video of our ArcFlash analysis series. This is a fault current through short circuit analysis. We can then apply the IEEE 1584 equations to be able to compute our arcing current. One thing to note is that when a fault occurs, the magnitude of the fault current at the faulted point is limited by the total impedance between the source and the fault point. So the whole essence of this video is to simplify our network, or basically see how we can simplify our network into what's called an impedance diagram, whereby each equipment will be represented in its equivalent impedance. In that way, we'll be able to compute the fault current, factoring in the total impedance contributing to the fault current. So let's get started. Now, like I said, this is part of our short circuit analysis. That will be part of our short circuit analysis. But now we'll be focusing more on the impedance diagram. So this is our network. It's a generating unit. It's a 150 megawatt rated unit. It is connected to a 400 kV grid through a generator transformer, which steps up 15.75 kV to the 400 kV. And that is working in parallel with our unit generator, a 150 megawatt generator with a terminal voltage of 15.75 kV. Then now this is how the rest of the unit in its equipment is supplied. It is through the unit transformer that steps down the 15.75 kV to 6.6 kV. And then that is what feeds our unit boards. We have unit board A and unit board B. Now, of course, they are fed by the common board through the station transformer, but just to simplify the system, I excluded that part for our analysis. So at our unit boards, that's where we find our 6.6 kV rated equipment. For instance, our feed water pump, and also we have our condensate pump, for this example. Now going downstream, we have our low voltage unit transformers. Now these supply our low voltage equipment. So these transformers step down 6.6 kV to 415 volts, supplying our two PC boards. That is our power center boards, power center board A and B. And these two boards are connected by a coupling breaker or a tie breaker, which in normal condition is open and closed. If one of the feeders, one of the transformers fails, then we can supply the other board through the other board by closing the second breaker. And then downstream of the power center boards, we have our MCC boards, our motor control center boards. And in this example, we have our boiler MCC. So this is just a typical layout of the generating unit. Now, just a quick recap on some of the fundamentals that will apply as we simplify this network into an impedance diagram. When we represent the impedance, we can represent it in polar form, and that will be the magnitude of the impedance at an angle theta. And in rectangular form, that will be the magnitude times cos theta plus j sine theta. Now, as we represent our impedance, we want to separate our resistance from the reactance. So how then can we represent this theta in terms of resistance and reactance? Going back to our impedance triangle, we have theta here. Adjacent to that, we have our resistance. Opposite that, we have our reactance, and then the hypotenuse is the impedance. So then how can we represent theta in terms of x and r? That will be through the tangent ratio. So tan of theta will be the opposite being our reactance divided by the adjacent being our resistance. Therefore, that makes theta to be equal to arctan or tan inverse x over r. And then substitute this theta into our equation. Then our impedance would then be the magnitude times cos arctan x over r plus j sine arctan x over r. This will be one of the fundamental equations we'll be applying representing our system as in the form of an impedance diagram. Now, one thing to note is that our equipment are in different ratings. So for us to be able to directly compare them, we need to have them at the common base. Since we'll be confirming these calculations using E-type normally uses a base of 100 MVA in computing short circuits. So our new MVA or our new short circuit MVA will then be 100 MVA. So this will be our new base. So we will be representing all impedances at this base. And how will we do that? We'll start off with our utility, which will be our first equipment or component of our system, being the reference component. So that will be our utility grid. Now, what is the impedance of our utility? It will be the old impedance multiplied by the new MVA base divided by the old MVA base multiply that by cos arctan x over r plus j sine arctan x over r. So this is typically the general formula we'll be applying for most of our equipment. So then the impedance, in substituting the values, the old impedance is 100% or 1 per unit. This is because the MVA of the utility was originally equal to the base MVA was originally equal to the short circuit MVA of the grid itself. So that will be the old impedance multiplied by the new MVA base, like we said, it will be 100 divided by the old MVA base of a utility was 1000. So we'll substitute that in here. And then going to our X over R ratio, the X over R ratio of our grid is 35. So that because tan inverse 35 plus J sine arctan, again the X over R 35. Now, once you input this in your calculator, you should get 0.002856 plus J 0.09996. So that's the equivalent impedance of our utility grid. Moving on to our second equipment, that would be the generator transformer. So the impedance of a generator transformer will be the old impedance. We have an impedance of 13%, an old MVA of 190 MVA, and an X over R ratio of 60. So applying that to our formula, we have 0.13 times the new MVA, which is 100, the old one being 190, multiply that by cos arctan, the X over R ratio was 16, right? 16 is 16 plus J sine arctan 16. So once you compute that in a calculator, you should get 0.004268 plus J 0.06829. So done with our generator transformer. Now moving on to our generator. What do we have for what data are we given for our generator? We have the MVA rating, we have the terminal voltage, the subtransient reactance, and also the X over R ratio. So this one is going to be a bit different because since we are given the subtransient impedance, our per unit reactance will be given by the subtransient impedance multiplied by the new MVA divided by the old MVA, which is 187.5. So we have our subtransient reactance is 13.9, so that would be 0.139 times 100 over 187.5. So our per unit reactance will be 0.0741. With that, we can then compute our per unit resistance, which will be our per unit reactance divided by the X over R ratio. And as you may remember, our X over R ratio was 10. That will be 0.0741 divided by 10. And that will be 0.00741. Therefore, the current impedance of our generator will then be represented as 0.00741 plus J 0.0741. And moving on to our next equipment, we have our unit transformer. It has an MVA rating of 23 MVA, impedance of 9%, and an X over R ratio of 12. So that will be what's supposed to be C, and then D. Okay, D, that will be our unit transformer. So the impedance of our unit transformer will be the impedance is 9%, right? 9% X over R ratio of 1223 MVA. So that would be 0.09 multiplied by the new MVA over the old one multiplied by cos arctan X over ratio of 12 plus J sine arctan 12. With that in our calculator, you should get 0.03249 plus J 0.38995. Okay, but it's start with our unit transformer. So then the next equipment will then be the next component will then be our cables. We have cables 1. In fact, I forgot to include the cable schedule. Okay. So we have cables, we have a number of cables. So we have for cables, before that I'll just include the cable schedule. So the cable schedule is as follows. Okay. So cable 1 to 6, 1 to 6. These are these are 3 single core conductors of size 70, with the length of 50. That's 50 meters. The length is in meters. It's 50 meters, and then you have the ohm per kilometer, which is 0.3424 plus J 0.1325. For cables 7 and 8, they are also 3 single core cables with size 70, but the length is 20 meters and the same ohm per kilometer. Try to make this neater. So then now we can proceed with computing the equivalent impedance of our cables. So for cables 1 up until 6, this is how we will compute the impedance. Um, the impedance will be given by, we have our new MVA base, multiply that with the ohm per kilometer, we multiply by our length, and then all these will be divided by the number of sets. And then all this will be divided by our line-to-line voltage, or the voltage of the bus that they are connected to, squared. So that means for cables 1 to 6, this is how it will look like. We have 100 AVA. We multiply that by, or with, 0.3424 plus J 0.1325. Multiply that by the length. We want it in kilometers. Since we are given it in meters, that will be 0.05. All these are divided by the number of sets for these cables. There are 3 sets. 3 sets of single core conductors. 3. And all these are divided by the voltage at which these are connected at. That is, all these cables are connected at so C1, cable C2, cable C3, C4, C5, and C6 are all connected at the 6.6 kV level. So that is the common voltage. So that will be divided by 6,600 volt squared. And that should give us the the equivalent impedance of our cable C1 and C6 should be, when you compute that, that should give you 0.0131 plus J 0.0051. Right. Then move on to cables 7 and 8. So for cable 7 and 8, same thing. The difference is the length, right? So that will be 100 MVA multiplied by the ohm per kilometer 0.3424 plus J 0.1325 multiplied by the length. It's 20 meters in kilometers. That will be 0.02. All this is divided by the number of sets. Also, 3 sets of single core conductors. That will be 3. All this divided by the voltage, which is voltage that these are connected is um, that is the 415 volt, 450 volt level. So the 415 volt squared. So that will be, when you punch that in your calculator, you should get 1.325 plus J 0.5129. Right. So we are done with our, okay, we still have a number of components. We have our motors, our low voltage unit transformers. Yeah, those two. So now going on to our, let's start off with our feed water pump motor. There's motor 1. It's feed water pump 1. Motor 1. So the impedance of motor 1 will then be a number of things to consider here. We have our, the motor is rated in this 2,500 horsepower. We need to convert that to kilowatts. And then we have our efficiency and our power factor there, our short circuit reactance, and also our exobar ratio. So this is how we will do this one. We have our short circuit impedance that is 15.385, right? So that will be 0.15385. We multiply that by the new MVA divided by the old, which is, you're not given the MVA, so we need to calculate that MVA with the data that we have. And what do we have? By the way, the underlying equation to calculating the MVA of our feed water pump is, that's the formula that we are applying. MVA is equal to kilowatt rating over the power factor multiplied by the efficiency of our machine. So this is what we'll be doing next, right? So what is our kilowatt rating? Mind you, we are given our rating in in horsepower, so we need to convert that to kilowatt. Applying the ratio of 1 horsepower is 0.7456 kilowatt. We'll then be able to convert that to kilowatts. So that would be 2.5 times 0.74 0.7456, right? 0.7456. Then all this is divided by, in fact, divided by the power factor. The power factor is 93%, the efficiency is 94. So that would be 0.93 times 0.94. Then all this is multiplied by cos arctan. That's our x over r ratio. X over r ratio is 32.6. 32.6 plus j sine 32.6. Therefore, the impedance of the equivalent impedance of our feed water pump is, when you compute that in your calculator, you should get 0.212 plus j 7.211. Right. Then now we'll move on to our second motor. Is a condensate pump motor, right? Yeah, condensate pump motor, or motor 2. So the equivalent impedance would then be, what is our, we have a short circuit reactance of 20%, x over ratio of 21.15. It's a 500 kilowatt rated pump. So with the efficiency of 93 and a power factor of 92%. So with all that data, we then have 0.20, multiply that by the new MVA base divided by, now again, remember the formula for computing our MVA given the kilowatt efficiency and the power factor. Since we have 500 kilowatt, that will be 0.5 divided by the efficiency, multiplying the power factor, so that will be 0.92 times 0.93. All this will be dividing the new MVA base. We multiply that by cos arctan, the impedance and the x over ratio 21.15 plus j sine 21.15. All right. And then the equivalent impedance would then be, calculate that in the calculator, you should get 1.6163 plus j 34.50. And next, we will move on to our last equipment, and these are equal. So these are our low voltage unit transformers. So for our low voltage low voltage unit transformers, A and B, we have a percentage impedance of 8%. These are 2000 kVA rated transformers with an X over R ratio of 7. So that will be 0.08 multiplied by the new MVA base over the old 2000 kVA. That's the equivalent in MVA. Multiply that by cos arctan 7, that's the X over R ratio, plus J sine arctan 7. So then that will be that should be 0.564 plus J 3.96. So those are the calculations which would then represent our equipment in their equivalent impedances. Now we're converting this network into a simplified diagram with the equivalent impedances. So that's what we will do here. We have our impedance diagram. Okay. Starting off from upstream, we have our source. Take our utility as our source, so that will be a positive source. And then we have our utility. That will be the impedance of our utility that's in series with the generator transformer, right? That will be the generator transformer. And these are in parallel with our unit generator. So this will be our unit generator. Remember, we have our unit generator here. I mean, unit transformer, sorry, unit transformer. This will be our unit transformer. This will feed our two boards, and unit board B, unit board A and B. But before that, we have two cables, right? So we need to show that this is cable 1, cable 2. So that the impedance of cable 1 and impedance of cable 2. And this will go to unit board A, unit board B. Now, what do we have at unit board A? We have feed water pump. That's our feed water pump. Right? That's that M1. And then, in fact, before that, we have the cable C3, right? We have cable C3. So there's the impedance of cable 3, and then in series with the impedance of our motor 1, feed water pump. And then right next to that, we have cable 4 in series with low voltage unit transformer. So this will be the impedance of cable 4. This will be our unit transformer. And then we have our PC board. And then what else do we have on the unit board B? We have cables 5. That is cable 5. We have the LV unit transformer on the B side. We represent them. Better notation. Say X from A, B. And then this feeds PC board B. And what else do we have? We have cable 7. It's cable 7. And here we have cable 8. Feeds boiler MCC. So then we are left with cable 6 in series with our condensing pump or motor 2 or motor number 2. Right. So then we can insert those figures. And insert those figures. So for our unit utility, we have 0.00 we have 0.002856 plus J 0.09996. Our generator 0.004268 plus 0.06829. Generator, we have 0.00741 plus J 0.0741. Our unit transformer or our HV unit transformer, we had 0.03249 plus J 0.38995. We calculated all these earlier, remember. There's our HV, there's our HV. And then now we go to cable. After our unit transformer, we have cable 1 and 2. And our cables 1 to 6 are, that's the impedance, 0.0131 plus J 0.0051. So that would be, this would be 0.0131, so plus J 0.0051. Same applies to this one, is C2 0.0131 plus J 0.0054. Same applies to C3. Same applies to C3. C4. C5. And C6. Right. Okay. And then now moving on to motor 1, the equivalent impedance of our feed water pump is 0.212 plus J 7.211. So that would be 0.212 plus J 7.211. Okay. And then for our LV transformers, those we calculated as 0.564 plus J 3.96. So that is okay. That is 0.564 plus J 3.96. Same applies to the one on unit board B, 0.564 plus J 3.96. Now lastly, we have motor 2, our condensate pump, and we calculated its impedance to be 1.6163 plus J 34.50. So do that. That is 1.6163 plus J 34.1850. And then lastly, we have our cables 7 and 8. We computed those, the impedances to be, is that 1.325 plus J 0.5129. So that is 1.325 plus 0.5129 J. So it applies to this 1.325 plus J 0.5129. So this is our impedance diagram, rather our system simplified into an impedance diagram. Now, on our next video, we'll then see how we use this to compute the fault current at unit board A. How then do we use this diagram to compute the fault current at unit board A, the fault inserted at unit board A? This is unit board B. Remember, all these impedances will then contribute to the fault current at unit board A. So we'll see how we use this to compute the fault current. Thank you so much for joining me in this video. I hope this helps. Join me in the next one. Thanks.